So, the agenda of today is about, or the lecture today is about eigenvalues. I need some light on the blackboard. Eigenvalues and eigenvectors. So I'll give a short intro about this, and then I'll discuss how to find eigenvalues. I'll talk about the characteristic matrix and also the characteristic polynomial. And I will discuss diagonalization of a matrix. And I'll end up by giving some perspectives. So, this is about linear maps. And we are given a linear map and it's between a vector space. The difference now is that it's a linear map, or both the domain and the codomain is the same vector space. So this is important. Although it is the same vector space, in order to illustrate, I draw it 2 times, and we have this linear map F, and say if you have a vector and then you have, say, f of v. So this is the image. So the question is now, is there a vector or an image that is parallel to the original vector? So I'm looking for a vector here that is parallel to the original vector. It could be in the same direction, or it could be in the opposite direction, but it should be parallel to the original vector. And if I should formulate this as a problem, the eigenvalue problem, then I ask the question, does a proper vector, that is a vector different from the 0 vector, and a number, lambda, exist so that the image of my vector is parallel, and that is, it's this number here times the vector itself. This is the condition of being parallel, that it is proportional to the vector v. So v should be a proper vector. Let's say if, well, let me just state what lambda is called. Then lambda is an eigenvalue and v is the corresponding eigenvector. To each lambda here, there's infinitely many eigenvectors. Because if you have an eigenvector, then you could multiply this vector by some constant k, and you will still have an eigenvector. So to each lambda there corresponds many eigenvectors. Also, the zero vector is a solution to this equation. If you put in 0 in this equation, then due to, you know that for a linear map, the image of the zero vector is 0, and so this is satisfied, and it is satisfied for any lambda. This this is not of interest. And the challenge here is that you have one equation, but in fact you have two unknowns. You have the eigenvalue and you have the eigenvector, and you have to determine both. And how we are going to do that, I'm going to show you. So I take an example here, and this is reflection in the x-axis. So let me draw this. You have, say, a vector v here, and then the reflection. So the image is like this. This distance is equal to this distance. And clearly, if you have a vector like this, these two vectors are not parallel. They are at an angle to each other. So the question is there vectors under this mapping that where the image is parallel? Let's draw the basic vectors. You have I here, and you have j here. If you look at the image of this basis vector, what is this equal to under this mapping? Yeah, I. And this you can write as 1 times I. So immediately you have found You have found eigenvalue, and you have an eigenvector. Are there any more? Let's try to take the image. So I could say that lambda 1 is equal to 1, and the corresponding eigenvector is I. I could take any vector that is parallel to I, and that is because it will be mapped. You see, any point on the real axis will be mapped into itself, so you can take any vector as the eigenvector. Now, if I take J, what is the image of J under this? Yeah? Minus J. Yeah. So, and this you can write as minus 1 times J. So we have a new eigenvalue, minus 1, and the corresponding eigenvector you could say is J. Now, all vectors on the real axis, or parallel to the real axis, because you know a vector is only due to convention that you draw it from the origin, but all vectors that are parallel to the real axis is mapped onto itself. So, in a sense, it's an eigenvector for this for this mapping. And this means that if we take all of the real axes and look at as a set of vectors, then this will be the set of eigenvectors. So this is simply span of the I vector. So this spanning will give you all the eigenvectors that corresponds to this eigenvalue. Similarly, we have is equal to span, or the spanning of J. So you have all the second axis here, or the J-axis. These are eigenvectors corresponding to minus 1. Now, let's look at a matrix version of this. And if you have a linear map, I could write it as does lambda and V exist such that a vector A times V is equal to lambda times V. This is, of course, a linear map, and if you have a linear map with a finite dimension, then you also have the mapping matrix if you choose basis. And the important thing here is that if you choose a basis here, then it's the same basis as here. So if this is n-dimensional, then the codomain is also n-dimensional. And this means that this matrix here is a square matrix. So, yeah?
Are we talking about the same domain, like domain and codomain being the same thing?
It's the same thing. It's only for convenience that I have put it twice up here. But it's actually mapped into itself. This is an n by n matrix, and this corresponds to the dimension of the domain and the codomain, that is n. So let me give you an example. I have this matrix here. It's 2 by 2 matrix with these elements 2, 5, 0, and -3. And I am I want to find say solutions to this equation. Let me just see if this is right. So I want to find a lambda that satisfies this equation. Now, if I choose V2 to be zero, or let me just say, I try to take the first vector and see what happens. I get then that the product of these is 2 equal to lambda and 1 times 0. And if I write, or if I choose lambda to be 2, then I get to 0 here. And this is okay. So one of the eigenvalues for this matrix here is 2. And you can see that an eigenvector is 1, 0. So we have lambda 1 equal to 2. And this corresponds to this eigenvector, and I have then that this is the span of this vector here. Now, in the afternoon there are a couple of exercises where you use GeoGebra in order to get a feeling for the geometrical solutions to the eigenvalue problem. And one of the problems is that you should actually try to find all the eigenvalues. Let me show this to you, because if you put in on a unit circle a vector v. Then this is mapped. I'd better use some colors here. So let's say you have the original vector is blue, like this. And then it is mapped into to this image here. And then you can try to move this vector along this circle, and at some positions there are parallel, and you can see that geometrically. But you do that this afternoon, but in order to find other eigenvalues of this in this example here, I give you this information in a triangular matrix. Lambda or the values in the diagonal are the eigenvalues. We have already seen that 2 is an eigenvalue, so we can read the second eigenvalue. Equal to span. And then, of course, you need an eigenvector. And if you look at this afternoon, you will find out that along this line here, the two vectors are parallel. So you can use this as and this is the line y equal to minus x. And this vector here, which is then an eigenvector, is minus 1, 1. So this eigenspace here, corresponding to the eigenvalue minus 3, is the spanning of this vector. Now, how do we actually find the E vectors or E values, eigenvalues? When we do that, we should consider this matrix here. This will turn up, and I'll just well, you'll see this a lot. This combination where A is the matrix that we want to find eigenvalues for. E is the identity matrix, that is a matrix where you only have ones in the diagonal, and then you have lambda. And when you interpret that, you have A, B, C, D. This is by way of example, 2 by 2 matrix, and then you have 1, 0, 0, 1. So when you write this out, you get, or you put it in one matrix, you get A minus lambda, and then B, and then C, and then D minus lambda. So when you're going to apply this formula here, you just write it like this. So lambda is subtracted from the diagonal. The second thing I'm going to show you is, or discuss with you, is can 0 be an eigenvalue? So the question is, can we find this is if 0 is an eigenvalue, you multiply it by the eigenvector and you get the 0 vector. So, is that possible? What if, what is the eigenspace corresponding to 0? Do you remember that? Yeah. It's a kernel. Yeah. So it's the kernel of F. And remember, a proper eigenvector is one that is different from 0. So it's only when I could write here, yes, 0 could be an eigenvalue, but only if the dimension of the kernel of F is greater than 0. If the dimension of the kernel is 0, then you only have the 0 vector in the kernel, and this is of no interest. But 0 can be an eigenvalue. I'll take a break now for 10 minutes.